So I'm going to tell you a little bit about self-duality in tropical geometry. This is part of a joint project with Sachi Hashimoto, Bernd Sturmfeld, and Raluca Vlad. And it's part of the paper Self-dual matroids from canonical curves. So let me tell you at the beginning a little bit about the motivation. So yeah. So the paper this talk is based on is called Self-dual matroids from canonical curves. So I want to give you a bit of the big picture before we start going into details. So I hope you've heard the term canonical curves before. If not, just think of them as particularly nice curves that are embedded into a PG-1. So they're curves of genus G. They live in a PG-1 and they have degree 2G-2. And they're particularly nice. They're not hyperelliptic. Okay, and if you have such a curve, you intersect it with a general hyperplane, what you will get is 2G-2 distinct points. And if you look at these points a bit more closely, you'll see that they are actually self-dual point configurations. So the term self-dual, what this exactly means, I will define later. But let me tell you that this type of point configurations was already studied in 1920 by Kobel. He called those associated point sets, and they were later studied also by Dolgachev and Ortland, who called them self-associated point configurations. Okay, so next step that we can do is, if we have these point configurations, we can choose homogeneous coordinates and write them in a matrix and look at the linear dependencies. And what we will get is a matroid that you should already be familiar with from Victoria's talk, right? So we have a matroid, and this matroid turns out to be self-dual, so a particular class of matroids. Okay, this is all nice. So we have arrows going one direction. Of course, now we want to understand, can we go the reverse direction? So if I have a self-dual matroid, can I realize it as a self-dual point configuration? And on the next step, of course, if you have your self-dual point configuration, is it possible to put a canonical curve passing through these points, which is called the question of lifting, okay? So this was the big picture that we had in mind when we started the project. There's also one more question turning up during this the work on this project, and that was, what if I have my self-dual point configuration that I said are distinct points, right? But what happens if I choose my hyperplane, for example, in a rather particular way, and I end up with a tangency point? So points are coming together. The point configuration is degenerating. And to understand this setting, we will need self-dual valuated matroids and tropical geometry. And this part, matroids, self-dual matroids, point configurations, degenerations, and valuated matroids is the part that I'm going to focus on in this talk. Okay, so let's start with some actual definitions. So what does it mean for a set of points to be self-dual? So first of all, we need two endpoints spanning Pn-1. So they're living in a projective space, and they're called self-dual if there exists a set of non-zero lambdas, lambda 1 to lambda 2, such that if I write my points in the columns of a matrix, this matrix equation holds. So the columns of a matrix times this diagonal matrix filled with all non-zero diagonal entries, and the transpose of my points gives me the zero matrix. Okay. Some of you, this might remind you of Gale duality, and this is exactly the correct notion. Okay. Okay, so let's look at an example. I've picked 4 points in P1, and I can find, for this example that I picked, 4 non-zero point lambdas, so lambda 1 to lambda 4, such that if I write them as the diagonal matrix in the middle, this matrix product will indeed give 0. Okay, now you can ask yourself, well, maybe this was just a lucky guess, you know, can I pick a different set of 4 points in P1 that are distinct? Is it still possible to find such a diagonal matrix? And indeed, it will always be possible for 4 points in P1. So this is part of interesting geometry that we see behind these self-dual point configurations. If you have 4 points in P1 that are distinct, it's always possible to find such a diagonal matrix. So all sets of 4 distinct 4 points in P1 are actually self-dual. So if we take a step up and look at a few more points, it becomes, of course, more complicated. And for 6 points in P2, the condition to be self-dual means that the points live on the same conic. So this is already a codimension 1 condition. And if we take one more step, it's also a nice geometric interpretation. 8 points in P3 are self-dual if they form a so-called Cayley Octad, which we will come to at the end of the talk again. Okay, so we have self-dual point configurations. We know what they are. We want to work with them a bit more. So we want to have some kind of parameter space that parameterizes our self-dual point configurations. And a setting that is very well suited for this is the Grassmannian. Okay, so we want to define the so-called self-dual Grassmannian. And for this, we need a few different ingredients. Okay, so basically I want to, just to go back, I want to translate this matrix equation into terms of, into an equation that holds on the level of the Grassmannian. So the first thing I want to understand is this diagonal matrix. And what does it do? Well, this matrix acts like column scaling on my points. This just corresponds to the torus action on the Grassmannian. That acts like, so lambda, again, here is a point that lives in the torus, and it acts on a point in the Grassmannian by multiplication of those entries that appear in the corresponding index of the Plücker coordinate. Okay, the next ingredient that we need is the so-called Hodge star map. Okay, so the Hodge star map in this particular case, because we look at the Grassmannian n to n, is an involution, and it maps P to P star, where P star is defined by this mysterious equation. Okay, so we need the sign of some permutation, and then we take the complementary index. The easiest way to understand this maybe is just to look at the example for n equal 3. So we have a point P with Plücker coordinates P123, P124, and so on till P456. And then its Hodge star is the point given by the coordinates P456, so the complementary index 2123, together with a certain sign. In the first case, this is positive. For the next coordinate, this is going to be negative, and so on. Okay. And how to understand this map? So what does it do? Basically, it maps an n-dimensional linear space in an ambient to n-dimensional space to its orthogonal complement. Okay, so P star is the Plücker vector corresponding to the orthogonal complement of the vector space that corresponds to P. And these are all the ingredients that we need to get the self-duality condition onto the level of the Grassmannian, because the matrix equation that we had before just translates now into P star equals lambda P. Okay, so why is this? Because we had this equation, my points, diagonal matrix, transpose of the points, lambda P was just the first set, right? And that it's that the output of this matrix equation is zero matrix just means that this is the orthogonal to the points P themselves. Okay, so the orthogonal space is given by lambda P. And as an example, this is the same point configuration that we chose at the start. We get the Plücker vector here. We let the lambdas act on it. We get this tropical point, and we also compute the Hodge star. And we see as projective points, these two are the same, right? They just differ by a factor of 2. So projectively, they are the same points. Okay. So now we know what the self-duality condition means on the level of the Grassmannian. And now I can define the self-dual Grassmannian. It's just the set of all points in the Grassmannian that are self-dual. And this is actually a variety. It's a rational variety, and it's a dimension n choose 2 plus 2n minus 1. Okay, so now we have a nice parameter space for these self-dual point configurations. But I also promised you matroids. So just a very brief recap of the definition of a matroid. So we've seen matroids already before in Victoria's talk. This is now just a matroid, not yet an evaluated matroid, just a matroid, okay? So we have a finite ground set E. In our case, this is always going to be 2n. And then the bases of the matroid that have to be a non-empty set that satisfies the basis exchange axiom, okay? But I want to focus particularly on self-dual matroids. So there is one more condition that we need. And this condition is that a basis of my matroid, if I have a basis of my matroid, then its complement is also going to be a basis of my matroid. So the set of bases is invariant under taking the complement. It's just going to be the same set. This condition, if you look into the literature, it's often also referred to as identically self-dual, as a matroid being identically self-dual. In this talk, I will just say self-dual for reasons of brevity. Okay, let's look at an example. So we take the ground set 1 to 4 and the bases set B1. Then this is a self-dual matroid because we can verify this very easily by just looking at it. We have the basis 1, 2, its complement is 3, 4. We have the basis 1, 3, the complement is 2, 4. It's again in my set of bases, so everything's fine. If, on the other hand, I look at the basis set B2, where I've added the basis 1, 4, you can check this still satisfies the basis exchange axiom. It's still a matroid, but now it's no longer self-dual because the complement of this set 1, 4 would be 2, 3, and it's not a basis of my matroid. Okay. Okay, so these are self-dual matroids. And now we want to realize these matroids as well as the linear dependencies of some matrix. And the realization space.
Alheydis,
yes.
I have a question.
Yeah.
So can you go? Yeah.
There is an echo somehow.
It's already done. Okay, I see. Sorry. Okay. I'll ask the question here then. So matroid is an independent system, right? So it should include an axiom that if you have a subset of any set that it's in matroid, then it should also be in the matroid. Am I right?
So there are different ways of defining a matroid. If I understood the question correctly, you're missing an axiom here in the list.
Yeah. Yeah.
Yeah. So I use these two axioms to define the matroid via its bases, which are the maximal independent sets. And these two axioms are enough if we define the matroid via its bases. So there's also the way of defining the matroid via its independent sets. In that case, I think, yes, the number of axioms is 3, and there are a subset of every independent set also has to be independent.
Yep.
And there is the way of defining it via circuits and via its flats and the rank function. There are a lot of different ways. I just picked the one with the bases because we are going to work mostly with the bases. And also it's the shortest of the ways of defining the matroid. So, because we just need these two axioms.
So are you saying that you don't have this inclusion property?
It holds. So it's these different ways of defining matroids are all equivalent. And there's a way of showing that. So an independent set is going to be, the independent sets here are going to be all the subsets of the elements in B. So B is the basis, so the maximal independent sets. So any subset, so here, these are the bases, right? any subset of these is going to be an independent set. So, okay, this is not very interesting because I have rank 2. So, but 1, as the set that just contains 1, is going to be an independent set because it's a subset of a basis.
Okay.
Does that answer the question?
Yep. Okay.
Okay.
Go on.
Good. Are there any other questions now that we're at it? Okay. Okay, then I'll continue. So we wanted now to have, we have these abstract concept of matroids. We want to realize them. That means I want to be able to write down a matrix, looking at the linear dependencies between the columns, and seeing my matroid captures exactly these linear dependencies. And the realization spaces of the matroids can also, again, be captured in the sense of the Grassmannian. So for the uniform matroid, which is the matroid that has no non-bases, so all the subsets of size n of 2n elements are bases of my matroid, then the realization space is just given as the open part of the Grassmannian, n2n, modulo the torus action. And the uniform matroid is a self-dual matroid because, well, for every basis element, the complement is again a basis because we have no non-bases. So I can also ask about self-dual realizations. So writing a matrix that captures the linear dependencies of my matroid that also satisfies the self-duality condition that we've seen before with the matrix and the diagonal matrix. And this realization space is the so-called self-dual realization space, and it's given by the open part of the self-dual Grassmannian, n2n, modulo the torus action. Of course, I can do this more generally for any kind of self-dual matroid of rank n. And then I will just look at the Grassmannian for this matroid. So the bases of the matroid give me those coordinate entries that are supposed to be non-zero, while everything else, all the other coordinates in the Plücke coordinates are going to be 0. And can do the same thing again for the self-dual realization space. And it's a natural question to ask whether these spaces are equal. Is this self-dual realization space always non-empty for any self-dual matroid? And we investigated this in a project for matroids up to rank 5. And since matroids up to rank 4 are already quite well understood, I'm only going to tell you today about our result for self-dual matrix of rank 5. So until we finished this project, there was no list of the self-dual matrix of rank 5 on 10 elements. So the one thing that we did is we computed all these matroids of rank 5 on 10 elements that are self-dual up to isomorphism, and there are 1,042. And we computed the dimensions of the realization space and of the self-dual realization space. So the self-dual realization space is very hard to compute. So you see here, there are a few of them were missing. They were just too expensive to calculate computationally. And one interesting result that we see from just these two tables is we have the number of not realizable matroids. So this is over characteristic 0. Of course, realization is always depending on which field we choose. We choose in characteristic 0 field. Here, the number of not realizable matroids is smaller than the number of not self-dually realizable matroids. So this already tells us that for rank 5 matroids, we see matroids that are self-dual, but cannot be realized in terms of a self-dual point configuration. Okay. And in general, the self-dual matroids, self-dual realization space will be smaller than the realization space. All this data is currently available on a math repo page to our project, and this collection of matroids will also soon be available on the database PolyDB in the collection. Yeah. Okay. So these are nice combinatorial results. I promised you a bit more tropical geometry. So let's see, we've understood a bit about self-dual matroids and their realizations in terms of self-dual point configurations. But now we want to look at what happens if these point configurations degenerate. Okay, and this is where self-dual valuated matroids will come in. But let's together look at an example. Okay, so we're starting with a very easy case, which is just 4 points in P1. Okay, if I have 4 points in P1, as a matroid, this will be the uniform matroid of rank 2 on 4 elements. And what can happen if my points degenerate? Basically, what happens is, the first thing that can happen is that 2 points will collide. Okay, so maybe my points 3 and 4 will collide. Now, if you show this picture to an algebraic geometer and you say, yeah, I was interested in distinct points. Now 2 of my points collide. What will I do? Well, the algebraic geometer will say, well, let's blow these points up, you know, let's blow them up. And now we get a new picture that looks nicely symmetric. And actually, you will get the same picture if you let like your other set of points collide, 1 and 2 instead of 3 and 4. You will see the same picture. And this already looks kind of nice in terms of what we want to see with respect to self-duality, right? Okay, but let's try to understand this from the perspective of matroids. So for 4 distinct points in P1, the matroid that I get is the uniform matroid. So all the bases, all the subsets of size 2 are bases. And I can draw for this the so-called matroid polytope, which we'll define in a second. But it looks like this. So every vertex is assigned 1 basis. Okay. And now what happens if I let 2 of my points collide, say 3 and 4? What happens is that the set 3, 4 is no longer a basis of my matroid. So I will only see the upper half of the pyramid. 1, 2, 1, 4, 2, 4, 3, 4, 2, 4, and 1, 3. And if, on the other hand, I let the points 1 and 2 collide, I will only see the lower half, yeah, the lower pyramid. And this blow-up picture kind of corresponds to looking at both these pyramids at the same time, but remembering that they're 2 separate things. So it's kind of, I have these 2 pyramids, I glue them together in the middle, but I remember that they were once 2. So it's a subdivision of the octahedron that I started with, okay? And this is where evaluated matroids come into play. Okay, so to be formal, I give you a definition of a matroid polytope. So you have your matroid on the ground set 2n. Then the matroid polytope is the convex hull of the sums of standard basis vectors for each basis of the matroid. This lives in R to the power of 2n. However, it actually lives in a hyperplane there. So we can visualize this as a polytope, full dimensional polytope in R to the power of 2n minus 1. Like before we did with this matroid on 4 elements, I visualized it as a 3-dimensional thing, even though actually it lives on a hyperplane in 4-dimensional space. Okay, now a subdivision of the matroid polytope is called a matroid subdivision if the cells are again all matroid polytopes. So all the vertices of the polytope correspond again to a matroid. And just to go back on the picture, here, this is the matroid polytope of the uniform matroid. And if I remember, if I just slice it into these 2 pyramids, then both of them are again going to be matroid polytopes because they correspond to those matroids with 1 non-basis, 3, 4, or 1, 2, respectively. Okay. Now it's nice. One thing that we want to do is, of course, also parameterize matroid subdivisions. And we only want to parameterize the nice matroid subdivisions, which are called regular matroid subdivisions. And the parameter space for these are Dressians. Regular subdivision just means that that subdivision is given by a height function, which I hope everybody has seen before. They're kind of popular when we're looking at tropical varieties, especially hypersurfaces. So, but if anybody has a question on these, I'm happy to elaborate. But I think everybody will be familiar. Okay, so the Dressian to n2n is the parameter space of the regular matroid subdivisions of the hypersimplex delta n2n, which is just the matroid polytope of the uniform matroid. And the elements in the Dressian are called valuated matroids. And those you know from Victoria's talk, they appear constantly there. Okay, so again, we look at valuated matroids. And then there is one more space, of course, that is important with respect to valuated matroids, and that's the tropical Grassmannian. And the tropical Grassmannian is the set of the realizable valuated matroids. So that it come directly from the Grassmannian end to end by tropicalization. Okay, so now we have a set of important spaces that we want to look at, the Dressian and the tropical Grassmannian. And we want to get back to the notion of self-duality. So how can we understand self-duality on this tropical level? Well, the very first thing, of course, I can do is I can go ahead and say, I'm taking the self-dual Grassmannian and I tropicalize that. That's a tropical variety, and we call it the self-dual tropical Grassmannian. Okay, that's one thing I can do. But there's also another thing that I can do. We remember we had this condition, P star equal lambda P, for points in the Grassmannian to be self-dual. And what I can do is I can say, I want to tropicalize this condition, okay? So let's do that. So we pick a point, Q in R to the 2n choose n, and say this is self-dual if Q minus Q star lives in the lineality space of the Dressian. So the lineality space of the Dressian is the same as the lineality space of the Grassmannian, the tropical Grassmannian, sorry. And this lineality space takes now the role that previously was held by the torus. So before we had P and P star are the same up to torus action. And now Q and Q star, the tropical Hodge star of Q, are the same up to lineality space. Okay. And naturally, this next thing is to say, okay, let's look at the self-dual points in the tropical Grassmannian and in the Dressian. And we denote these sets with this upper SD for self-dual. Okay, but now I have three spaces that a priori tell me something about self-duality in tropical geometry, right? And what we need to understand is, of course, how do these three spaces correspond to each other? And this is a proposition from our paper that we have this containment chain, okay? So the tropical, let's look at this. So the tropicalization of the self-dual Grassmannian N2N is a subset of the self-dual points of the tropical Grassmannian. And then this self-dual points of the tropical Grassmannian are again a subset of the self-dual valuated matroids in the Dressian. So this inclusion at the very end is kind of the easiest because we know the tropical Grassmannian sits inside the Dressian. So if we're now cutting with this self-duality condition, which corresponds to intersecting with the linear space, of course, the containment is going to stay, right? It's not going to go away. Okay, the first containment comes from the fact that tropicalization and intersection does not commute completely, but it keeps one inclusion. And this is the tropicalization of the intersection of the Grassmannian with self-duality, and it's contained in the tropicalization of the Grassmannian intersected with a self-duality condition. So this is nice, but there's still something missing, right? We want to know, are these containments actually strict? And unfortunately, I cannot give you a general answer to this, but we see how this behaves for at least small n. And from there, we may, at least for this last inclusion, we will later be able to make a guess on how this general will look like. Okay. So before we do that, let's just first look at what exactly are these points, these self-dual valuated matroids. So if we're fixing a self-dual valuated matroid, it's a point in the Dressian, in the self-dual Dressian. And then we can look at the set of matroids of rank n that appear in the associated matroid subdivision. Remember, a valuated matroid induces a subdivision of the hypersimplex, and then all these cells will again be matroid polytopes, so we can associate matroids. Okay, then this proposition tells us that a matroid appears in this collection if and only if its dual is also in the collection. Okay, so the collection of matroids we see from the matroid subdivision of a self-dual valuated matroid is self-dual in itself. So the matroids in this collection might not be actual self-dual matroids, but the dual will appear somewhere else in the collection. And well, this is actually quite easy to see, because that Q and being self-dual for the valuated matroid means that Q and Q star are the same up to linearity. So that means they induce the same subdivision of the hypersimplex. And since M will appear in the set of Q and its dual appears in the subdivision of Q star, of course, since they are the same subdivisions, they both will appear. There is a question.
Excuse me. Yeah, there is a question from Georg.
So maybe it's trivial or just said this, but you said the word self-dual so often that I lost track. So sorry. If I have a, no, it's just due to the topic, I guess. So if I have a valuated matroid, which like in the direction n to n, such that in the induced subdivision, each cell is self-dual, do I have a self-dual valuated matroid?
Not necessarily. So, yeah, so this is something we'll actually come, maybe this might be clearer when we look at an example later, but so the fact is, so the collection of matroids that we see in the matroid subdivision does not need to be, like, all these matroids in there don't have to be self-dual.
Okay.
But the dual of the matroid is again going to be in the collection. And on the other hand, just because this condition is satisfied does not necessarily mean that my point is that this point Q lives actually in the self-dual part of the Dressian. Because of course there are different points in the Dressian that give me the same subdivision, but the condition that Q minus Q star lives in the linearity space is definitely a lower dimensional condition than the whole cone that gives me the same matroid subdivision.
Yeah, okay, thank you.
Hi,
yes,
this is Alex. Just follow-up comment or question. Alheydis, you tell me if I have this right, but a matroid is self-dual if and only if it's polytope, sorry, not if and only if a matroid is self-dual, then its polytope contains 1/2, 1/2, 1/2, etc. Correct?
Let me think 1 second. I think what you mean is a stability condition.
Maybe it's a stability condition. You just mean something elementary, right?
Not all self-dual matroids are stable. Most of them are, but not all of them.
Yeah, I mean something just more elementary. That the point, all of whose coordinates are 1/2, right? That's the average of the indicator vectors of any two complementary bases. So Georg was saying, what if every cell is self-dual? Well, that means 1/2, 1/2, 1/2 is in every cell, right? So that's going to be very rare. That's going to be very rare, but it's still, so I guess that in that case you have, if it's in the interior, well, but yeah, but the fact remains that what we need is also that this height function that gives me the subdivision needs to satisfy Q minus Q star is in the linearity space. Right. So that's one more condition than just looking. We cannot just look at the subdivision. We also need to remember the height function. Yes, thanks.
Okay. Okay.
Continue.
So was there more questions?
No, there are no more questions.
Okay, good. How much time have I left?
You have at least 10 to 15 minutes, something like that.
Okay, good.
That means you certainly have.
Yeah. Okay. So let's look at an example again of degenerating point configurations. So since 4 points on P1, we've already looked at them kind of. So let's go to 6 points on a conic in P2, and I've chosen 6 points. They live on a conic. I want to degenerate them. Okay, so I have this parameter T. Of course, for all the tropical geometers here, these are points in a Puiseux series. Yeah, I have the valuation that usually take when I look at the field of Poisson series. But let's just be very naive and say, let's just be t our parameter, and we want to let t go to 0. What will happen is that I will see at the end only 3 tuples of points. So 1 and 2 will collide, 3 and 4, and also 5 and 6 will go to the same point. And now if I look at the point in the Grassmannian, I can do the same. I can let t go to 0, and I see everything that survives are those entries that have this red 2, okay, this red entry. And if I look at the Plücke coordinates, at the indices corresponding to these things, I will see these are exactly the bases of the matroid that it will have if I look at these 3 tuples of points. And at the same time, if I look at the tropical Plücke vector, which is the last one that you see here, it's the tropical Plücke vector to this, the entries with the red 2 now, of course, are the ones that go to 0. And this is a positive, non-negative and Plücke vector that gives me a matroid subdivision. And all the entries that are set to 0 kind of give me one cell of this matroid subdivision. Okay, and it's exactly the one that corresponds to the degenerate case where I pretend t is 0. Okay, that's nice. So I see one cell, one special cell out of my matroid subdivision here. But of course, I have projective points that I actually start with, right? I have 6 points in projective space. So I can choose different column scaling for my points, right? So I can choose different representative modulo the torus action. One that might not look quite as nice, like the one that we see here, right? And I can do exactly the same thing again. Yeah, I can see kind of what happens if t goes to 0. And we want to look at, of course, in this case, rather the point in the Grassmannian than the actual matrix. And I see that a bunch of different coordinates survive this time, right? So 1, 2, 3 will still be a basis of the matroid after degeneration. And I see, of course, the same thing here very nicely for the tropical Plücke vector, right? I see different entries are to 0, but it's still a non-negative vector. So I can still say, okay, the zeros, they will be the basis of a cell of my matroid subdivision. And since the 2 points are only different by the linearity space, because the matrices are only different by torus action, I know these 2 points give me the same matroid subdivision, but they kind of highlight different cells that correspond to different degenerations. Because in this case here, I see, since 1, 2, 3 is still a basis, that 1 and 2, after letting t go to 0, they stay distinct. But again, 3 and 4 and 5 and 6 will collide. Okay, and the picture for this behavior is here. So this is the tight span of the matroid subdivision. What does that mean? It means that every of these black circles corresponds to a maximal dimensional polytope, matroid polytope in the matroid subdivision. And these matroid polytopes intersect in a codimension in one phase if they are connected by an edge. And this interior is a codimension 2 cell that is shared by all the 6 maximal dimensional polytopes. And to each of these polytopes, I can associate a degeneration of my point configuration. And I see the one with the 3 tuples of collided points is the interior cell. And the other one where 1 and 2 stay distinct and 3 and 4 and 5 and 6 collide correspond to this matroid polytope on the, upper right, okay? Okay, so this is nice, but we want to understand this more generally than just for this one example. And the way to do this is, of course, we're looking at the tropical Grassmannian 3.6. And so by Speyer and Sturmfels from 24 in their paper, the tropical Grassmannian, they computed the tropical Grassmannian 3.6. And in particular, they analyzed it. So there are 3 types of rays. They're called E, F, and G, and there are up to S6 symmetry, 7 types of maximal cones that are spanned by these different rays. And here I've drawn the tight spans for the corresponding matroid subdivisions that you can also find in their paper. And now, of course, to each of these black dots, belongs rank n matroid in the matroid subdivision. So one thing I can do, of course, is I can sit down, I can look at all these 7 types and see, okay, I have this matroid here. Let's take the dual. Can I find the dual inside of this matroid subdivision somewhere? And if I do that, it turns out, well, of course, well, this one will work. The last one here with 3 Fs and 2 Gs, that's the picture that we've just seen in the example before. And the only other subdivision that satisfies this condition is the type EE, this type EEFFA, okay? And for all the others, there will be at least like one matroid for which the dual is not contained in the subdivision. So they definitely cannot be part of the tropical soft-dual Grassmannian. Yes, so the picture is, what we know is there are 2, so there should be a trop in front of the SGr36 here. So of course, these are the maximal cones of the tropical soft-dual Grassmannian. And there are 2 types, this hexagon that we've already looked at, and this other shape where we also see associated degenerations of points that sometimes are different, that there are different ones appearing from the ones that we see in the hexagon, but also some of them are the same, like the interior here and here. Okay, but one more thing that we have to keep in mind is that the soft-dual Grassmannian is a codimension 1 variety of the Grassmannian 3/6. Okay, for n equals 3, it's a codimension 1 variety. So of course, we're not going to see the whole cone that corresponds to these types, but just a hyperplane slice. And to understand how exactly this looks like, so we have a theorem, an analysis of this tropical soft-dual Grassmannian. So first thing is we wanted to understand from the beginning that this proposition with the containment chain. And in this case, for 3/6, these containments are all equalities. Okay, so the soft-dual tropical Grassmannian is a balanced fan of pure dimension 8. It has a 6-dimensional linearity space, and it coincides with a set of self-dual points in the tropical Grassmannian, which is the same as the self-dual points in the Dressian. Okay, so this last equation, tropical Grassmannian, self-dual, and Dressian self-dual, that this is the same is not really surprising because we know the tropical Grassmannian and the Dressian for 3/6 are the same. But up here, so this is answering one of the questions that we asked before, right? Tropicalizing the self-duality condition first or after tropicalizing and then intersecting. In this case, it doesn't matter. It's just going to give me the same space. And there is one more really nice feature to this, and this is that we can parameterize this tropical soft-dual Grassmannian 3/6 by means of the tree space trop GR26. So there is an classical algebraic geometry. There is the so-called Pachter-Speyer map, which maps from the Grassmannian 2/6 into the Grassmannian 3/6, which is, and this is based basically on Veronese embedding. And this map is a monomial map. And this is very nice because when we tropicalize a monomial map, we get a linear map. And in our case, we get a linear isomorphism onto the tropical self-dual Grassmannian. So we can parameterize the tropical self-dual Grassmannian by the way of trees with 6 leaves. And in particular, if we're modding out by the linearity space, we get a pointed fan of that's 2-dimensional over that's 3-dimensional over the 2-dimensional simplicial complex with 25 vertices, 105 edges, and 105 triangles. Okay. One disclaimer I should make here is that in this theorem, we look at all these fans, so these different fans with their unique coarsest fan structure. So in these cases, all these tropical varieties have a unique coarsest fan structure, which in general is not true, but for these ones, it works. And the unique coarsest fan structure is the same for all of these spaces. Okay. Yes, and so one more thing I want to tell you about this is that there are 2 types of these triangles, of these maximal cells. We've already seen these in terms of the tropical self-dual Grassmannian, right? We've seen these 2 different types of matroid subdivisions, and they correspond to the 2 different types of trees that we see in the tropical Grassmannian 2/6. There's the caterpillar tree that corresponds to this matroid subdivision, and the snowflake tree that corresponds to the hexagon-shaped matroid subdivision. Another nice fact that we've seen when we computed the tropical self-dual Grassmannian 3.6 is that the intersection with the tropical Grassmannian 3.6 goes like this for these maximal cones. So instead of these 4 different rays that spanned my 4-dimensional cone in the tropical Grassmannian, we now see 3 rays. Naturally, it's like 1 dimension smaller. And one of the rays for this type is the sum of the 2 rays that we've seen before. And this is a particularly it's a self-dual sum, right? Because I have 1, 2, 3 for the first index and 4, 5, 6 for the second. So this ray again is self-dual. And for the type FFFGG, we cut exactly by those 3 rays that are self-dual themselves again, these Fs, while the Gs are just completely, they vanish. They're not in the self-dual locus. Okay, that's everything on the tropical Grassmannian 3.6. And now, of course, we can ask ourselves, well, if it works that nicely, can we do something similar for the self-dual Grassmannian 4.8? And for this, we need to take a step back and look at the algebraic geometry setting. And this were for 8 points in P3, Cayley Octads, as you might remember from the start. Okay, Cayley Octads, they arise first as the complete intersection of 3 quadric surfaces. They are already in the work by Dolgachev and Orland from 1988, I think. Okay, and they appeared again in work by Plaumann, Sturmfels, and Vincent from 2011. And they proved that if we have points in general position, then the Cayley octad is determined already by 7 of its 8 points. So general linear position, I'm choosing the first 5 points as a projective basis. I have 2 more points, then I can compute the 8th point by using this rational functions that we see here. Of course, general position also includes that I here in this formula is not accidentally dividing by 0, right? Okay. So this is a really nice result because 7 points give me already the 8th point. That means in terms of the Grassmannian that we have a map from the Grassmannian 4.7 into the self-dual Grassmannian 4.8. This is a birational map because I'm looking here at an open subset where my map is defined. Okay, and I'm always going to end up in the self-dual Grassmannian 4.8. So this is a nice start for parametrizing. And in our paper, we computed this map. We call it Cayley Octad map on this level of the Grassmannian. So a point from the Grassmannian 4.7 will be mapped to the Grassmannian 4.8 in a way so that we ensure it's going to be a self-dual point. Okay, so we're keeping those coordinates where 8 does not appear in the index, and the one where 8 appears, we modify in a certain way so that it fits together with the self-duality condition. Okay, and for that we need these xi, which again are binomials in terms of the Plücke coordinates that only contain 1 to 7 in their indices. And now, well, what we would love to do is to use this in order to parameterize the tropical self-dual Grassmannian 4.8. So we do the naive thing, tropicalizing this map. So we take a point in the Dressian 4.7 and we map it to the QIs when 8 is not in the index and to the tropicalization of this formula we had seen before. Qi minus the sum of these xi. But it turns out there is a problem with this naive tropicalization because this is in general not going to be well defined. So how does this happen? Well, we pick a point, a matrix, a 4x7 matrix. We compute the tropical, the point of the tropical Grassmannian, and we plug it into this naive tropicalization. And it turns out it's not even in the Dressian 4.8 because all these, we have the Dressian is determined, as we heard from Victoria, right, by these 3-term Plücke relations. And we just pick one of these 3-term Plücke relations, and we need the minimum to be achieved at least twice. And if we plug in the values for this specific point, it turns out we get the minimum only once and not twice. So it does not live in the Dressian. And of course, the reason for this is that in this map that we've seen before, the xi are binomials, right? So they cancellations can appear. It's not as nice as with the Pachter-Spire map that was monomial and we tropicalize it and we get a linear map. Here, cancellations can appear, and this is exactly what's happening in this case. Cancellations appear, and we do not get what we would love to see. However, so this is still open. And if anybody of you has any ideas on how to fix this problem, I would really like to talk to you about this. However, we can still make first steps in understanding how tropical self-dual Grassmannian 4.8 looks like. And this is going to be the last part of my talk. We have this proposition in our paper, and it tells us that the tropical self-dual Grassmannian 4.8, well, no surprise, it's a balanced fan. It is pure dimension 16 with 7-dimensional linearity space. This we can all get from algebraic geometry, right? But also we get this last inclusion to be strict in this chain of containments that we've seen before, right? So we know the tropical self-dual Grassmannian sits inside the self-dual points of the tropical Grassmannian, and this one will be strictly smaller than the self-dual evaluated matroids. And how do we prove this? So we pick a self-dual matroid of rank 4 on 8 elements that is not realizable over C. So in our project, this matroid came up when we looked at all the realization spaces for rank 4 that I did not show to you. I only showed you the rank 5 results. There was one matroid that's not realizable over C. Okay, so we pick this matroid and we extend it to a matroid subdivision of the hypersimplex. Okay, so we construct basically a point in the self-dual Dressian by setting each coordinate to 0 if the index is a basis of my matroid, and to 1, sorry, and to 1 otherwise. Okay, then since the matroid I started with is self-dual, this point Q will again be a self-dual evaluated matroid. And further, my matroid M will be a cell of the matroid subdivision. Now there's a very, very nice result by Brandt and Spire that tells us if we have a matroid subdivision and there is a matroid in it that's not realizable over C, then this evaluated matroid is not realizable itself over C. So this point Q lives in the self-dual Dressian, but it will not live in the self-dual points of the tropical Grassmannian. So we've seen this inclusion is strict, and I assume that this will be something that we'll also see for higher rank matroids, that this inclusion is strict in general. However, this first inclusion is still open, and I'm very curious about this. And this is the end of my talk. Thanks for your attention.